In this video, we'll be talking all about coordinate systems. And when we're surveying, we're essentially trying to put numbers in terms of measurements and angles and things, and have them spatially referenced to each other and other things that are known. There's three main coordinate systems we'll be looking at. The first one is the ECEF coordinate system, the Earth-centered, Earth-fixed coordinate system. And here we're looking essentially at an XYZ or a Cartesian understanding of where a particular point is on the surface of the Earth. We define two planes. One plane is defined by the X and Y axes, and we call that the mean equatorial plane. It's essentially a plane that goes right through the equator, which separates the northern and southern hemispheres. And then we have a plane that goes between our x-axis and our z-axis. And that plane is the zero meridian plane. That plane lines up with the prime meridian. The longitude at that point is 0 degrees. And it aligns with the Royal Observatory in Greenwich in London. Having said that, it's an arbitrary point that was chosen on consensus to be a good point to put the 0 point. The 0 point has to be somewhere. Our GPS systems use this ECEF frame of reference. Our next coordinate system is probably one that you're more familiar with, which is the latitude, longitude, and altitude coordinate system. Here we have a picture of the Earth, and we see our longitude as it goes around the Earth, and our latitude and different latitude points north of the equator and south of the equator. This latitude and longitude system is what we normally see on maps. You'll see it on mailways, for example, or on topographic maps if you're going bushwalking. And we typically record values in latitude and longitude in terms of degrees, minutes, and seconds. This is our classic coordinate system that we've used for hundreds of years. And our GPS systems will also give us a latitude and longitude that they've calculated based on the ECEF data. We can define our latitude as a point north or south of our equator line. If it's north, we refer to that as a positive latitude point. If it's south, we refer to that as a negative latitude point. Australia is south of the equator, so we would have a negative latitude point. And likewise, with our longitude, as we go east from our prime meridian, which is Greenwich in London, we adopt a positive longitude. And as we go left from our prime meridian, we adopt a negative longitude. So for Australia, our latitude is negative and our longitude is positive. And then we have our height. Now, this will depend partly on terrain, but also partly because the Earth is not a perfect sphere. It's not a ball, it's an ellipsoid. And so our height the height of that ellipsoid from the center of the Earth will actually change depending where you are on the ellipsoid surface. One thing that can trip people up is there's different ways of expressing this latitude and longitude. And here's the main three. Firstly, it's decimal degrees. So you specify your degrees, like 25 degrees or -5 degrees, and then you have a decimal point and the decimal of that degree. So no specifying minutes and seconds or anything like that. You're specifying the decimal value. Our next one, the DMS format, is where we specify degrees, minutes, and seconds. This is very commonly seen on maps, for example. And our final one, DMM, we specify degrees, then we specify minutes and our decimal minutes, where we have the minutes and then a decimal point and whatever fractional value of those minutes that we have. Now there's online calculators, but you can fairly easily multiply and divide to convert between these different values. Now back to the shape of the Earth. I mentioned it's not spherical, it's an ellipsoid. And so our longitude, if we go around our longitude, that's a longer distance, approximately 40,075 kilometers, than if we go right around one of our latitude values, which is about 40,008 kilometers. And so we can specify a semi-major axis, which goes out to along our equator line, and a semi-minor axis, which goes along our polar line. And if we specify our semi-major and our semi-minor axis as A and B respectively, we can derive some geometrical formulas for things like the flattening and the eccentricity of, basically with our eccentricity, we're looking at how much our ellipse, which is what makes up our ellipsoid as we revolve it around the axis, how much that deviates from a perfect circle. Now we also have three different methods of defining our latitude and longitude. The first one is the geocentric one. Now in our geocentric, we reference both our latitude and longitude to our ECEF. Now with our ECEF, we define our center position for ESEF as the center of the Earth, the very center of that ellipsoid. Our next form is the geodetic form, and this is the one that's most commonly used. In the geodetic form, we reference our longitude as we go around to our ESEF through the center of the Earth, as we did previously. But with our latitude, what we do is, rather than going through the center of the Earth, remember this isn't a sphere, which is a perfect circle. What we do is we have a plane and we work out what the value of that plane value is from where we are on our ellipsoid. So sometimes it might go through the center of the Earth, but as we move at different points around our ellipsoid, we'll have a different perpendicular line from a plane that would be on the surface of our ellipsoid. Our final one is our astronomical way of specifying latitude and longitude. And once again, our longitude is referenced to our ESEF data, so through the center of the Earth, through the center of that pole. But our latitude data here is referenced based on gravity. Now, you might think that gravity would go through the center of the Earth, but it doesn't. And where gravity points us in terms of our vector can change based on where we are on the Earth. So in that diagram above there, you see our three different, the geocentric, all through the center of the Earth, the geodetic, one through the center of the Earth for our longitude, and one through wherever our perpendicular line comes down from the surface of our ellipse. And finally, our astronomical, where we're looking at where our gravity vector is pulling us. Now, previously I mentioned WGS84. WGS84 stands for the World Geodetic System 84. There are previous ones like WGS77, but WGS84 is the most commonly used and the one that we use world over. And WGS84 is what our GPS satellites are referenced to, and it defines the size and shape of our ellipsoid. So within WGS84, we have an ellipsoid with our semi-major axis here and our semi-minor axis here in A and B, along with our eccentricity squared value, which, remember, is a measure of how much this ellipse varies from a perfect circle. Now, we've talked a lot about latitude and longitude, but what about height? Well, we have this thing called geodetic height. And geodetic height is where we're trying to work out what's the difference between the surface of our ellipsoid to going directly up from there, the height on a particular spot on the Earth, whether that be at the top of a mountain or whether it be deep in a valley or whether it be somewhere in between. So that height is directly perpendicular up from the surface of our ellipsoid. Now, the ellipsoid is a mathematical construct. It's based on those A and B values based on our WGS84 system. And so our geodetic height might be above that ellipsoid, in which case it would be a positive value, or it might be below, in which case it might be a negative value, for example, if we were in a deep valley. And so it's important to realize our geodetic height isn't just the height above the surface of the Earth or the height above the mean sea level. It's above that WGS84 reference point of where that ellipsoid is.